Qiang. He is the head of the Huawei Noah's Ark Lab, which I found out, maybe I'm stealing your show, but the Noah's Ark has to do with the flood of data, and the Noah's Ark rescue Noah and his family from the flood, so that was a connection. But he's also a professor at the Hong Kong University of Science and Technology. And before that, he got his PhD in 1989 in computer science at University of Maryland at College Park. And after that, moved to University of Waterloo in Ontario and was a professor there for 6 years. And from there, moved to Simon Fraser University, so our side of Canada, I guess I should say, in British Columbia. And then I assume after that, you moved to Hong Kong and then I guess just was it last year was when the lab started out. And that lab, which right now is 50 researchers, and he tells me they want to get up to 150. So a lot of recruiting to do there. Looking at his bio, Dr. Qiang is a fellow of most of the major AI organizations. He's on the editorial board of many of the major AI publications. He's chaired or co-chaired most of the major AI conferences, and he's chairing IGERT in 2015, which is in Buenos Aires. IGERT is the International Joint Conference for Artificial Intelligence, kind of the top worldwide AI conference. His research interests, as you might gather, are mainly artificial intelligence, data mining, machine learning, planning, and activity recognition, which is a big area here. And today he's going to talk about AI applied to user modeling and how to apply that to social and mobile computing.
Thank you, Larry. Thank you, Dan, for inviting me. Nice to meet everybody. So this is my talk, and I hope to learn a lot from you. This morning has been exciting, and I found out a lot of very interesting work here. So let's start. Okay, so first of all, continuing from the introduction Larry gave, so this is the structure of this new lab in Hong Kong. And so besides the researchers, we also have a lot of software engineers to actually build things. And we are divided into these vertical areas, natural language processing, data mining, social media, and mobile intelligence, that is putting AI into the mobile phone, and also theory. And we already started on several projects based on all of these areas. So Huawei is a major telecommunication equipment provider, and naturally we are interested in diagnosis and data mining on the data streams. So how to save cost in telecom industry. In natural language processing, we are interested in how to facilitate human-computer interaction, human interaction in different languages. And then we have a project which is to build the next generation mobile phone. And we are trying to imagine different dimensions in which the mobile phone can be intelligent, can be part of the human, part of your family, and can grow with you, can learn from you. There's a project called Big Money, which is how to expand into different areas of banking industry and theory. Okay, so I noticed there are lots of graduate students here. If you are interested in internship and in the very exotic Far East, you can come to Hong Kong for a period of time. Okay, so let's get started. In this talk, I'm going to go through a series of talks. Some of them have been presented at conferences, others are ongoing, to give you a full picture of the kind of work we are doing here. The general theme of the work is learning user models and learning it from where we find most data is. That is today in social media. This work, the first work I'm going to describe, relates to a social networking company similar to Facebook. And in fact, it's the Chinese version of mirror image of Facebook is called Ren Ren, which essentially means everybody, and has about the same number of people as Facebook has. And this one is about how to use user models to discover spammers. Okay, so we know that there are some people who try to make money from everything, right? And including social media. and so, you know, there are people who disguise themselves as ordinary users, but they are actually there for some purpose, such as commercial purpose, sending out a massive amount of advertisement. And they change from place to place. Sometimes they change back to normal. And so how do you figure them out? And how do you improve the quality of the general social network? And so this is the issue of this research. Okay. Now, in fact, this problem is a very serious problem. So, for example, just from the Facebook quarterly earnings report, it said that about 1% of the users are spammers, and they actually generate a lot of loss in the company. Same thing with Ren, this Chinese company. And so it is in their interest to find out who these people are and to do something about it. Okay. Now, so the current approach by the company is they have a large call center. So there are some experts, hundreds of people there, and sifting through all the activities and trying to identify who is a normal user, who is not. And as we know, this kind of operation cannot be scaled up because, you know, expensive human labor, humans cannot pay attention 100% of the time, and so on. So it's in the interest of this to employ an automatic system that can sift through all the data and can give a ranking of potential spammers. Okay, and so we view this as a binary classification problem where we can identify user as either a spammer or not a spammer and associate it with a probability. And so the question is really how to build a profile of a spammer to represent it as a vector on which we can apply a classification model. Okay, so building the features of this vector is the issue. Okay, now we don't want to intrude into people and have a lot of conversation and ask, you know, whether you did this, whether you did that. We just want to observe from the side and looking at all the activities and trying to figure out whether these activities are out of the norm, okay, are out of the ordinary. And this thing is done not on the user side. So not from a, typically, you know, a user has a lot of friends and you can build maybe a Bayesian classifier to classify which friend might be and might not be a spammer. But we actually have the luxury of observing all the data and all the connections from the server side. Actually, I sent a student to do intern with the company, so he has access to all the data. Okay, and it's important to use social relationships to improve the accuracy. And this is because each individual's data can be rather sparse, just like with our mobile applications. Okay, so talking about activities, what can the activities be? Many people here use Facebook, Twitter, and so on. So we are already familiar with the activities. They can be as simple as a click, okay? Or the use of an app or a message sent from a person to another. Although we don't want to analyze the content of the message, we know the metadata about the message, the size, who to send to, when, and where. And if you summarize this, there are really thousands of different activities. Follow a person, befriend a person, having a conversation, and so on. Okay, so all of these give you, so massive people, 99% are normal people, and there's 1% are spammers. So how do you distinguish between the two? Now, in fact, the social relationship between the people turns out to be important, right? So we can build it into a user-user relationship graph, but some of them are spammers. This graph is very sparse, okay? So for example, if represented in matrix form. Now, just from this, we still cannot tell spammers who the spammers are. We have to have a way to find out who is a neighbor, and while being a neighbor, what kind of things they do, okay? So mathematically, here I want to throw in a little math. If you just have a relationship like this in a graphical form, then you can build the classification model as the following steps. Simply, you build a vector for each user. Okay, you represent a user using some important dimensions. You can think of PCA, for example, like in this user activity graph. Each row is a user vector, but as we understand this, each row is extremely sparse. Okay, so we cannot simply use these raw data as the data to do the classification. So we want to use the user-user relation also to help regulate. In other words, we want to discover a subspace which is more condensed and more representative of the user. And this is where it comes in. So people who are familiar with PCA, for example, as is done in most of the machine learning work, is trying to find a subspace that is really important. Okay, similar approach is taken here. We want to factorize a very large relationship matrix into a compact matrix, and that includes two kinds of information: the user-user relation, and also the user activity. Okay, and then if we can do that, we can find a factor U which represents the users, and V which represents the activities. Okay, but then how do we distinguish spammers from the rest of the people? For this, we need some additional knowledge to so-called regularize the graph. And the intuition is like this. So we have a lot of users with a lot of activities, which is represented by a cloud here. And spammers, so the first question we want to ask is, are spammers friends of spammers? Do they form a network of bad people, like a gang? Or do they hide within normal people, and as if, because they don't want to be found out? And so there are some studies. We found one study, just recent study, that says spammers are friends of spammers usually. But after we analyzed this huge network, we found out that's not true in this social network, at least in this Chinese social network. In other words, spammers are usually friends of normal people, and they hide. They are loners. Okay, they do things alone, and they are you cannot tell from their neighborhood information. So that makes the situation very tricky. Okay, because you cannot tell use this neighboring information to find a whole bunch of them. You have to sift through one by one. So we want to build this information into our regularization framework to state that normal users are usually friends of normal users, and plus if we know somebody is a spammer, which is indicated by the Y here, now we do have some labeled spammers found out by experts. Okay, so we use these as labels, and then we find out if they are spammers, we enforce that they are usually not friends of other spammers. And so we can build this into the right-hand side of the equation. Okay. Then after that, we have a loss function which we use to decompose the activity network into U and V. And then we want to also make sure that our model, which is represented by W here, is a simple model. Okay, so we want to, on the far right-hand side, we want to make sure that this W is small in size. Okay, this is typical of the Occam's razor principle. Okay, so typically we are done here. Okay, it's because we have included all the information we wanted. So our goal is to find out this U matrix on each row of which is a condensed subspace of the user vector. And so that has to reduce the overall error rate, as well as enforcing the fact that the classification gives us the right result, which is represented on the right. And also in the first term there, J sub S, there we enforce that spammers are connected in the right way in the network. Okay, so this work then took a portion of a sample of the Renren network, which is sampled from 160 million users, and then we took 30,000 of the accounts, in which we took 1,600 activities in total, and then ran through them. Okay, so there are activities like visiting an album, visit a bulletin board, visit a blog, read a blog, and retweet, and so on. But there are a lot of other more sparse activities in the long tail. And then we took a portion of the spammers and tried to classify them, use them as training data. So in the end, the evaluation is based on precision recall type of information retrieval type. Essentially allow us to find out how precise the model is and how complete the model is at the same time. Okay, so to put the results in simple terms, this approach allows to reduce the false positive significantly as compared to the baseline work, which is used by the company using people mostly. Okay, and at the same time can catch more spammers, about 3% more, which now these numbers may not seem big, but in actual numbers they are significant. Okay, so this is the first work. There's a lot of details which appeared in this AAAI 12 paper. Okay, the second work is also related to social networks, but it takes a different angle. Okay, it's titled Collaborative Classification of Social Activities in Microblogs. Now, before I start on this, I should tell you why we are interested in mining activities from social media. You can see a lot of things that people do every day, like in their daily living, for example. And of course, we are interested in monitoring and helping people in the home environment. So the first thing, of course, is for us to understand their activity patterns. But as soon as you are starting to build the model, you will find that training data is in short supply. Okay, and so that's why we turn our attention to social media and try to find out whether we can discover a large portion of the model from the social media. And that can really alleviate our difficulty in terms of getting the very precious physical space label data. Okay, so there are lots of things that people talk about, like, you know, I watched this TV show, I listened to this music, I read this book, I read this news, I'm doing piano, I'm doing sports. So people talk about it in Twitter and in any social media, right, in Facebook and so on. And so there's a lot of things we can build. So for example, we can build a Markov model which can tell us, after doing one activity, typically what other activities do they do, okay? And after going to a location, what is the most frequent activities they do at a certain time, in a certain season, for a certain purpose, okay? Now, if you try to discover a lot of this, you will find that they are widespread. They are, the data is in more abundance. So this is our motivation. So, but the question is, can you actually do that? Now, when we actually look at each individual's, so this gives you some examples, right? Now, so when you look at each individual's text, so this is a tweet. For example, I just made homemade sweet potato and so on. So this is something related to eating, right? And so you will put that in the category of maybe daily living, maybe having dinner or something. And in another case, a person said, very happy with the result, can't wait to work on this track. And this is more related to attending a conference. So there are several issues here. One is the natural language processing issue of how to recognize synonyms. Especially in social media, people use very cryptic words. But there's even more serious problem, which is for each individual, the data is very sparse. Okay, they don't talk about going to a conference all the time. Maybe they in 3 months they talk about it once. So you really have to leverage a lot of similar users' activities in order to boost the data population. Okay, so even though we have lots of data for free, the data, each individual's data is of very low quality. So these are the difficulties. But what can actually help us is that these users are connected. Okay, so the connection gives us a lot of strength in terms of building similarity between the users. And so that really is the countermeasure that we can use to solve this sparsity problem. And that's why we call this work collaborative classification. Now, here I should note that activity recognition in the social media is different from event detection in the social media. Event detection in social media, if you Google this term, you will find a lot of papers from very early on in all kinds of conferences areas. So for example, you can discover from Twitter messages that maybe there's a major event happening at a certain concert hall or stadium. And so here, for the event, you're interested in something at the more grand level, okay? You are not so interested in each individual granularity, but something that is aggregate, a massively aggregated activity. So in discovering activities on the social media, we have to pay attention to more finer details of signals. Okay, so here we say that for the individual users, it's user-centric. Okay, so things can be different from person to person, whereas event detection is more collective and aggregated. Okay, and here I mentioned that the social activities are sparse, and they use different synonyms to mean the same thing. Okay, so putting it together, we want to make use of the social relationship. We want to preserve the individuality. And so putting this together, one solution we thought about is what we call gradient boosting, which is you use your neighbor's data to help improve your quality and vice versa. Okay, so you can do this back and forth, and the whole network is helping each other all the time. Hopefully, the collective quality will improve, and this is what we call gradient boosting. Okay, so in other words, classifiers are competing for a large margin solution. Each person is a classifier. They are connected, and they also collaborate with each other through voting. Friends are voting on each other's data. They learn from each other. And so this is a kind of knowledge transfer from people to people, okay, between the neighbors. Okay, now having this intuition, now we can put this in a framework. The framework has two components. One is, of course, we want to classify a person's activity into one or in a number of categories. Okay, so maybe here we have 5 possible categories, and we can say the person is walking, is talking about sports, talking about entertainment, talking about working, home activities, and none of the above. Okay, so and so here the graph shows 4 people, and each person has a number of tweets. That's represented by these vertical bars. Okay, and so some of them may be connected to each other, and that's represented by the links here. Now, so back to the original, so we want to build a optimization function which takes into account both type of objective. One is it should be accurate and in terms of classification on each individual, and so that's what the box stands for. And then the second part is on collaboration, which I will show in the next slide. So on the first part, we want each classifier to be defined by the margin of the model has on classifying its own data, and that can be represented by this function here. Okay, and the second part is on preserving the similarity between neighbors. So we want to look at 2 classifiers and ask whether they give similar results. If they are neighbors of each other, say one follow another, or even closer if they follow each other, then we wish their classification classifier to be similar. That is, when acted on similar data, they should give similar result. If they are far away from each other, that is, if their distance in terms of similarity is very low, the distance is far, then we don't care if they are similar or not. Okay, so the second part actually reinforces this idea. And also, if then we can let them help each other, right? So to form some kind of transfer learning. But if they belong to different communities, like on the left-hand side, there is a drinking club, and on the right-hand side, there is a academic group. And so if they are far away from each other and with only very sparse connection, then we hope their relationship is not very strong. Okay, so this kind of transfer between different communities that are far from each other will be discouraged in our similarity function. Okay. Now having had this idea, then we have to build into the operation a method for collaboration. Okay. Now this method is actually quite straightforward. It's borrowed. The idea is borrowed from boosting. Okay. In boosting, we have generations of classifiers, one building on the mistakes made in the previous generation. And then as we go on, we can see that each classifier is helping to correct the mistakes the previous classifiers made. So therefore, collectively, you're getting more and more accurate. And here we are trying to do the same, except the generations are spread spatially. Okay? So we have a neighborhood of U1, the user U1. Now we can do two things. One is to define the pseudo label on my data and learn from the voting on my data. That is, I take my data as the test data, and each of my neighbors' model as the potential model, and let them vote on my data. And this vote actually gives me some idea on whether I'm doing the right thing. Okay, because the majority can be a mirror image or a baseline which I can compare my model to. Okay. Similarly, I can export my data to my neighbors and let my neighbors act on them. Okay. So this idea allows data to be spread, to be shared, and allows the classifier also to be shared in this way. Okay. Now putting this together, we have this idea called collaborative boosting. Okay, so then we did some experiment, and we defined, so here we only, in the experiment, we only use 3 categories, but in our larger scale experiment, we use 20 different categories. So we hope to refine that down to even finer details. But for this experiment with 3 categories, we had about 50,000 users with, about on average, there are 24 neighbors and a number of messages sent to each other in this random sample. Okay, and then we compared with a large number of baselines, including a traditional classifier without using either the neighbor's data or the model, some semi-supervised learning approach, some collective classification approach, which still there's no collaboration, but everybody is doing classification on their own data, and then comparing the results to each other. Okay, and multitask learning, and finally collaborative classification, which is what we call social boost. This method is called social boost. Now, one thing we found is that there are other methods which can be equally accurate or roughly equally accurate, but one thing is with this social boost, the result is very robust on different categories that we look at individually and across different data, different groups of data. There are other results on efficiency. The method can should be run just like an ADA boost. It should run to convergence. It actually converges pretty quickly within 10 iterations, and so the method is both scalable and robust. Okay, so this is what we discovered. So we are hoping to use this method to actually help with our activity recognition in the physical space, which is something I'm going to talk about at the end of this talk. So this is just recognizing whether somebody is talking about some activities we are interested in. Okay. Now, related to this work is another work where we try to build a agent system on the microblogging website. And so this is the idea. Now, so to motivate this work, actually, what occurred to us is the social media, such as Twitter. Now, in China, the corresponding system is called Weibo, which means literally microblogging. Now, and it has about the same number of users. It's very actively, heavily used in a similar manner, except it's all in Chinese. So we are thinking about how we can build a natural language Turing test in the space of microblogs. So the idea is this, right? So in the original Turing test, we have a machine and a human locked in separate rooms, and a judge will ask questions and get answers. And after a number of questions, if you cannot tell the human apart from the machine, then the machine has passed the Turing test, right? And here we thought, okay, so on the microblog, there are millions of people, and if you design one of those people and put it in there, and nobody can tell if it's a fake person, then it's a microblog Turing test, right? And so whether that's possible, let's give a try. So here we are trying to build a system that emulates one or a group of people on a certain dimension of interest, such as machine learning or activity recognition. So this person, this agent is more like an assistant to a real person. So an application of it would be, an agent living in your mobile phone and can observe all your activities on the phone, including short messages. And over time, it will learn to be able to compose short messages for you. And with your permission, it will send, when you are driving, when you are busy, or when you are unable to type. Wouldn't that be nice, right? So that's one obvious application. Okay, so we are hoping to do this, but the first thing that comes to mind is to build different user models. If you have a large array of user models, then for any new person coming in, we can then observe this person for a while, and then we can say, you belong to the student group, or you belong to the working person's group. Now, better yet, maybe this person is a mixture of these user models. Sometimes the person looks like a student, sometimes like a working person, sometimes like a tourist. So let's try to represent that naturally and let it learn different facets of the person. Now, of course, if you have an assistant like that, you have to first solve the problem of natural language generation, which is really hard, and we are not experts in that area. But one observation is that since the microblogging world, the Twitter has such long history and already generated so much data, we in generating a response to a statement. Okay, on the left-hand side is a statement, on the right-hand side is a response. In generating a response, we don't need to actually generate, because for almost literally any statement, there's some proper response hidden in the space already, because by virtue of the massive data that and number of people who are very similar to each other. Okay, so the natural language generation problem becomes a matching problem, and we call this semantic matching. So similar tweets will have similar comments. For this, we have this. For this, we have this. And we can generate something which is very similar to those generated by human. Okay. So with this idea, and also some idea I'm going to present in a moment on modeling user topic models, we built this, we call this Weibo Hall. Hall came from the movie 2001, and so we try to generate this microblog to be like a Hall computer. Okay, and as I said, Microblog Hall. And so this was in back in February. I think it had 400 people who are following him, and a larger number, almost half of them, actually thought this was a real person, and actually, like Microsoft listed it as a fan of Microsoft website, even. Okay, and now I think it's in thousands. So. People following this. We have one for machine learning. So it actually emulates some prominent people who tweet machine learning news. We have one on real estate, and there's a larger group of people following that. We have some people on just food and dining and so on. Okay, so I had a video, but because I copied something, like maybe if I have time, I'll show you the video. But let's go to some statistics. We did some study. It's hard to see this pie chart here, but the people in the user study commented favorably on the performance of this. But I want to get into the technical aspect of the model more. So I'll skip this part, just telling you that it's actually doing well. Okay. Now, so how did it do so well? In fact, we have built a topic model which we call user message model, or UMM. And in this, we build different aspects of the user interest. Okay, so this is the operation of the user to training for the user topic model. One thing on NA micromedia is the sparseness of each individual's data. And here we solve it by imposing a bias on the user tweet topics, okay? By noticing some basic information about the user and imposing this prior model. And another aspect is we don't want the person to be the agent to be a nerd, okay, to only focus on one area and not talk about others. So we want to have reasonable topic diversity, and that's imposed by learning this parameter theta, okay. And furthermore, since the system is to operate on millions of users, we have to use a distributed algorithm to operate this training. And so we partitioned the learning into different groups according to different neighborhood and different topic areas, and applied Gibbs sampling on MapReduce in different iterations, and found this to be really effective because it doesn't require that many iterations to finish. Okay. Right, so here are some results. As I mentioned, we particularly try to model some very prominent tweeters, one in real estate area, one is a chief executive officer of a search engine company who tweets massive tweets each day. Maybe every hour there's like 1 or 2 tweets, and these people simply tweet every aspect of their life and all the opinions, and we check with different users and to see if they are true representations of these people because they are famous, and they think so. Okay, and we analyze the different topics of messages generated based on one area, the Beijing area tweet, and found in this period of time the topics are what people expected. Okay, so the system is still operating, and there are like 10 different agents trying to learn in these different topic areas, and we are trying to the next step would be to move it into a automated messaging system, which is equipped with speech. So you can give, for example, it generates a tweet for a person and say, do you want to tweet this? If you confirm, then it automatically tweets it. And for people who are on short messaging system, say if you are driving and you are late, then we want the system to compose a short message for you and ask you permission, upon which we'll send the message to the waiting party automatically. Okay, so hopefully we'll have some experiments on this. Now finally, this is something more related to the research that you are doing here, mobile user modeling, and this is really also what I've been interested all along, how to represent a physical user's activity and build it into some device and make it widespread use. Okay. Now here I want to start with a challenge which was held last year. It's called Nokia Mobile Data Contest. So in this contest, what they did was in the Geneva Lake area, they collected about 200 people's data over about 2 years. And the data is very rich because each person is handed a mobile phone, a Nokia phone, and there's a wide variety of sensors that are collected, accelerometer, GPS, phone logs, not the content, but the meta information, the charging information, charging status, the Wi-Fi, and so on. Okay, so all of these over a long period of time. And then they ask the following questions in 3 different tasks. The first one is, where are you? And this, the meaning is where you are at, what do you often do at that place? Okay, so this is known as the semantic place prediction. The second is a prediction problem. Now, I know you are here. Where do you go next? I know you are here. What do you do next? And third one is, who are you? Okay, can I know your gender? Can I know your maybe even your major, your type of work? And how much can I know about you just from the phone data? Now, in addition, it has an open challenge and say, given this data, what can you do for me? Okay, so this is a really interesting and very intellectually stimulating challenge. Now, in fact, my team got #1 in 2 of the 3 tasks. And what they did was, I'm going to describe in the next, but I would say that the open challenge was actually very exciting because one of the open challenge winners came from McGill or somewhere, maybe McGill. And it's actually auto-generating stories based on sensors. So the idea is you carry your phone all day. At the end of the day, it generates a diary for you. Okay, and then of course the diary can be rather boring, but you can go in. You have the freedom of going in and revise it. And this is reported in MIT Tech Review, and so it's rather prominent. Now I'm going to tell you a little bit about what allowed us to win these 2 tasks. Remember, the first task was semantic place prediction, and the last one is demographic prediction. Now, this demographic prediction actually predicted gender, age, maybe even number of cars you have at home, your salary level, and so on. Now, how accurate can this be? Actually, very accurate, about 90% and above. Okay, and so question like, how do you tell whether the person is a male or female just by the person carrying the phone around? In fact, a very telling feature is where you put the phone. For male, we usually put the phone in a pocket. For female, in a purse. Okay, so that's generate different accelerometer features for the person. Okay, next time you may want to fool your phone. Right, where are you? So these things can all be done using very simple algorithm. But the real trick is how do you, from existing data, how do you generate lots and lots of features? We generated about 20,000 features for each task. And that allowed us to have a very large margin from the next team. So how we generated the features is first we designed different categories of features, say in a time dimension, in a space dimension, and then within each one you can generate different hierarchies of segments, right? And all of these in combination can give you different features. So some features are, the point is you never know which feature is important, okay? So what we learned from this challenge is that feature generation is going to be the determining factor in accurate activity recognition. Okay, so this is it. Then at the lab, we try to take this idea further. For example, we have the phone and we want to generate a lot of data from these sensors, but the method that Nokia used was to give the phone to people to volunteer and let them collect the data. Now this method is hardly scalable, okay? Because you can do that once, you can interest some students, but they only represent a segment of the society, and you cannot do that in a sustained manner. So what we try to do here is to go into a very interesting approach known as human computation, is to design incentives for people to engage in some joint activity with the phone, and do that in a sustainable manner, that is over a long period of time, in a continuous manner. So we try different things. One thing is called the ePet project. We designed this app, which is a little pet, can be a dog, and can simulate everything you do. So all you need to do is to carry the phone, and when you do your exercise, this pet will do exercise as long as you tell the pet that you are doing the exercise. When you are eating, the pet is also eating, but then you have to tell the pet that you are eating in order to activate the fact that the pet is eating. Now, why do you have incentive to do this? Because the more data you give to this dog or cat, the better it grows. And so it's like data becomes dog food, okay, or cat food. And if you want your pet to be strong and beautiful, and maybe even have children, then you want to keep feeding data to it. So then we analyzed the users who used it. So initially we got about 10,000 users. We just throw it onto the app market and observe how many people register. And there are lots of children who actually love this game, and they play a lot. But they try to do things not in the way we intended. we wanted the pet to accurately reflect the person's activity, but the person is actually playing hide and seek with the dog. And so in the end, the activities are not very useful, for machine learning. But it's interesting. Then we designed another game, and this was at the beginning of this year. It's called One Day. So the idea is we follow the open challenge solution in generating a diary for each person. But instead of just generating a diary, in order to generate the diary, of course, you have to enter a lot of labels for what you are doing. And you keep doing that. The more you do that, the more diary, the more accurate the diary can be, okay? And the more activities, contents can be in the diary. At the end of the day, we actually generate a cartoon to show that what you have done in this day. In a movie, you can make the movie 1 minute. You can actually send the movie to your mother and share your daily activity in a cartoon form. So lots of people love this, and still there are hundreds of people today using this. And from this, we actually got a lot more high quality data. But in the end, it's not as, it didn't snowball as we expected. We thought from maybe initially we got 10,000 users, and we hoped the next day it will be 20,000, but it didn't happen. And the reason, part of the reason we thought was because people are recording their daily activities in little pieces like Twitter, microblogging, rather than a diary. Diary is something our parents do. So we have to think about something new, and we are at this stage. But it gives us some very good initial data to start with. Okay. Another thing is, going back to the first talk, the first part of the talk is how to discover activities from social media. And once we discover these activities, we can discover models of the activities. For example, we can discover build a Markov model of people's activity. After doing this, you typically do that. If you do these things in a row, the next activity is likely to be this. Now, if we have that kind of activity, we can move it to the physical world. And this is in the physical world, trying to analyze the following things, right? So point of interest at this location, what do people do mostly? And activities, what are the temporal distribution, spatial distribution of people's activity? And we found this to be quite effective. But one challenge which we face is to join different activities, to relate different activities together. For example, there's maybe a closer relation between the activity of running and weightlifting as compared to eating and doing sports, and having different distance measures between activities. This shows the PET, the ePET model. On the left-hand side is the conversation with the people. On the right-hand side is the game model. On the client side and on the server side as well. Okay, and this shows you a bigger, more detailed interface of the one-day agent which can do the diary. All right. Now, this is the last part. So with all that knowledge, we are trying to, so what we are aiming at is something we call a lifelong learning agent. So we try to, so this is the concept we try to build into the next generation phone. The phone will become a partner throughout your life. Maybe you change the hardware, but the software always stays with you, okay, through cloud computing, for example. And in childhood, in young adulthood, it serves different purposes. For example, in childhood, it goes through intelligence development, like this, and And young adulthood, it satisfies your social needs, and in the middle adulthood, work efficiency, and in the older adulthood, you develop better your inner life and health. And we call it MOCA because it stands for Mobile Knowledge Assistant, and also sounds like a coffee drink, and hopefully the user will be addicted to it. Okay, so this cartoon shows what we are trying to build, and we hope to build actually we have built the activity recognition model, and next we are trying to build a model for each phase of a person's life. And in young adulthood, this story shows what we are trying to do. So for example, the computer is watching a child, monitoring a child's activity, and trying to, from time to time, trying to teach a new concept about safety, okay? But then at some point found the child to be distracted by some toys and realized in teaching I have to be aligned with the child's interest. And so designed something which shows in maybe a three-dimensional projection of a car and get the child attended to it, okay? So then when the child plays the car, the child is part of the whole story in which you are trying to teach safety. Okay, so everybody is happy in the end. The parents have more time to do other things, and the child gets more intelligent. Okay, so that's what we are trying to build into this, into different scenarios. Okay, so let me end here. Right, so what I have gone through are different examples, but there's one theme, that is data mining is playing a major role in social media, social networks, and mobile computing. But data mining requires data, okay? So when we face the social media and social networks, the data are relational data, although very sparse, but there's a lot of things we can do. We can design new machine learning algorithms, and then we can use the data and the knowledge we gain in social media to help with the physical world to build our model and for activity recognition and lifelong machine learning. Okay, so that's the end of my talk. Thank you very much.